vocab, and then we'll talk about your graphs a little bit. These aren't all the vocab words you have on your sheet. You have a couple more. So, monomial. Who can tell me what a monomial is? Ella.
A real number, a variable, or a product of a real number and one or more variables with only their exponents.
Good. Okay, so it's basically nothing being added or subtracted, but the product of any numbers with variables that could be to any whole number exponents. So, for example, a monomial would be 3x. Oops. Yeah. 3x squared is an example of a monomial, okay? 5 is also an example of a monomial, okay? 5 plus x is not an example of a monomial, okay? 5 plus x would be a binomial, okay, because it would have two terms. All right, now, right below monomial, your guys' list says degree of monomial, okay? What is the degree of this monomial, 3x squared? Yeah? 2. Good. Okay, the degree is the highest power or the sum of the exponents. If I had a y in here with this, that's still a monomial, and now its degree would be 3 because 2 powers from x and 1 from y. Okay? So the degree of a monomial is either just the one exponent or the sum of the exponents on the variables of that one term. Okay? What's a polynomial then? Carson? The sum of the exponents in the monomial is the degree of the monomial. Vito? Good. So a monomial is a polynomial, but a polynomial can also have more than one monomial being added together. So that is a polynomial, right? It has a monomial, another monomial, another monomial, okay? We call those terms of our polynomial. What is the degree of the polynomial? Carson?
The value of the greatest exponent in the polynomial.
Good. The value of the greatest exponent in the polynomial. So, again, 1 is a monomial. What's the degree of 1? No. 0, because it has no variables, okay? Degree of 0. So this is its own monomial with its own degree of 0. This is another monomial, 2x. What is the degree of 2x? 1, because it has an x to the power. This is another monomial, 3x squared. What's the degree of that? 2. These three monomials being added together create one entire polynomial, okay? And the degree of this polynomial is not 3, 2. So each monomial has its own degree. To pick the degree of the polynomial, you just pick out the largest one. Okay? So this monomial had degree 2. That's the largest one. Then the degree of the whole thing is 2. Okay? Does that make sense to everybody? Okay. All right. So then let's look at, okay, how do you write a polynomial function in standard form? Kira? Good. Okay. So ours up here has it too. So she said like 2x to the third plus something x squared plus something x plus a constant. Notice the order of the terms doesn't matter, but if you're writing it in standard form, it does. We generally put the monomial that has the highest degree first and then work our way down. Okay? All right. Turning points. What are turning points? Who hasn't answered me yet? All these people. Jonathan.
A point at which the derivative changes sign.
Ooh, yeah, okay. So that's an intense one. So a point at which the derivative changes sign. So in calculus, you guys will learn about these things called derivatives, which measure rate of change. Rate of change is kind of like slope, but you can't really, a parabola doesn't have slope, but at each point you could draw a little line that has a slope that matches up with that point. So in calculus, the way they would look at this is they would say a turning point is the place where the derivative changes sign, because the derivative right here would be like the slope of this line, which would be positive, but the derivative right here would be the slope of this line, which would be negative. So the point where it turns around is the point where it switched from being a positive to a negative derivative. Okay? But you guys don't technically have to know derivatives yet. Carson?
Would that be just where it's 0?
Yes. The turning point would have a derivative of 0. Mm-hmm. Kira? Good. So turning points are going to be maximums or minimums. Now, some of you might argue this is a turning point and it's not a maximum for the graph overall. But there's two types of maximums in mathematics. There are maximums, like the absolute maximum, and then there are maximums like relative maximums. In this area, is it a maximum? So this turning point isn't a maximum for this function overall, but is it a maximum in this little area of the graph? Yes. Okay, so turning points can be relative maximums and minimums. Okay, yeah, Foster? They're like vertexes. You could use that, sure. Okay. Yeah, Sandy? Good. So at this point, the function was increasing as you move across the graph, and then when it hits the turning point, all of a sudden now it is decreasing. So just like what Jonathan said about the derivative, even though we don't totally know what that is, that it changes the direction, that's because our graph is going from increasing to decreasing or decreasing to increasing, okay? And that's why the graph turns around. That's what we refer to as a turning point. All right, what about end behavior of the graph? Foster? Oh, sorry. Hannah? Good. As you look at the graph from the far left and the far right, which direction does the graph just kind of straighten out and end up going? Does it end up going towards infinity, or does it end up going towards negative infinity, right? Because eventually, after all the turning around, these graphs kind of just shoot off in one direction. So those are our end behaviors, okay? All right, so then you guys graphed some stuff at the bottom. Just briefly, I'm not going to put everything in the right place, but as we go through this, here's what I want you to think. What patterns do you see in the end behavior? I want you to think about degree. So all 6 of your functions have an equation and they have a degree listed. Okay? I want to build a relationship between what the degree can tell me about the end behaviors, the maximum number of turning points, and the maximum number of solutions. Well? Oh, okay. That's fine. Whatever. Typo. All right. So for this first graph, f of x equals 2, it's constant. You guys should have had a horizontal line at 2. Okay. The second graph, f of x equals 3 over 2x minus 3, you should have had a line with a positive slope. For the third graph, you should have had a parabola, right? Okay. I'm not going to draw it accurately. I don't have it on my calculator. Okay, what about these things we've never graphed before? What does this fourth graph look like? Carson?
It's like a roller coaster.
Okay. Sure. Like this?
It curves twice and
Okay, has 2 turning points. Good use of vocabulary. Okay, what about this quartic function? What did it look like? Joy? Okay, it looks a lot like a parabola, but it has some weird little distorted thing at the end, right? At some point, it kind of goes like this. Weird. Okay. We'll figure out why it does that. Lauren? Uh-huh. Okay. Like this? Did I go too many? No? Okay. All right. So let's talk about this. Okay? First of all, look at the end behaviors of the graph. Do you see any pattern between degree and end behavior? Joy? Uh-huh. Okay. Good. Okay, so your pre-calc teachers have told me to make a very clear something right here. You're going to learn in pre-calc about even and odd functions. That's not what we're learning about right now. We are learning about degree and what the degree tells us about a function. So can we all agree right now that the whole entire conversation we have is about degree? Okay? I'm not saying this is an even function or an odd function. I am saying this function has a degree that is an even or an odd number. Are we good with that? Okay. So what Joy said is the functions that have a degree that is even appear to behave more like a parabola, whereas the functions that have a degree that is odd appear to have different behaviors at their ends. So look, right here, degree 5. Okay? With a degree of 5, the end behavior goes in two different directions, right? But with a degree of 4, it behaved more like a parabola, right? The end behaviors are the same. Okay? So basically what we can notice is if the degree is even, the end behaviors are expected to be the same, right? They're either both going up or both going down, this kind of thing. Whereas when the degree of the function is odd, the end behaviors are in different directions at different ends of the graph. Now, which way? Well, kind of depends on some other factors that we'll look at later. Okay? All right, what about number of turning points? Did anybody see a relationship between the degrees of these functions and the maximum number of turning points that they could have? Carson?
For the odd ones, the even ones stay the same. For the odd ones, for every odd turn, it got, was it 2 more turning points? Maybe 1 more.
2 more turning points or 1 more? Well, let's look through. So this function had degree 5. How many turning points did it have? 4. And then this one had degree 4. How many turning points did it have? 1, maybe 2. Yeah, because this weird thing happened here. This had degree 3. How many turning points did it have? 2. Okay. Our parabola has degree 2, and how many turning points does it have? 1. Okay, so can anybody kind of make a theory about what's happening here? Vito?
For every odd number degree, there's almost 2.
Yeah. You can actually say that about even numbers too. You can't guarantee that they turn around. Like you might say, no, Ms. Dahl, this did not have 3 turning points for our quartic. I agree with you. But I didn't say how many does it have for sure. I said what's the maximum number of times it could turn around. So this quartic could turn around how many times? 3. Does this one turn around 3 times? No, but it could. Okay? Depending on if it was a different quartic function that they put up there. Okay? What about number of solutions? What am I talking about when I say number of solutions? Joseph? Yeah, so we'll say number of real solutions. We'll look at places where it crosses the x-axis. Do you see any relationship between the number of solutions and the degree of the function? Lauren?
Maximum number of solutions.
Good. So our quadratic, our parabola, what was the maximum number of times it could cross the x-axis? 2, because the maximum number of times it could turn around is 1, but that makes possible 2 crossings. Now, does it for sure cross the x-axis 2 times every time? No. But is that the maximum number of times? Yes. But then when you move up to a cubic, and now you can turn around twice, you can go through the x-axis, turn around, come through it again, and you can turn around again and go back through it again. So you could possibly go through the x-axis 3 times. Okay? Are you for sure going to cross the x-axis 3 times? No. Okay. All right. So do we kind of see patterns that are coming up there? All right, so we're going to practice a couple of skills. On the back side, you see example 1. So part A just says, write the polynomial in standard form. What did we say it was to write it in standard form? Sandy? Good. The monomial with the greatest degree down to the monomial with the least degree. Okay, so we're going to go with, let's see, x cubed is the greatest degree. So that's negative 6x cubed. The next greatest is x squared, so 3x squared. Then 5x, and then 4. So there's this same polynomial. All I've done is rearrange it and write it in standard form. If there were like terms, we could combine like terms, but there weren't any. Part B says to name the polynomial based on its degree. So this polynomial as a whole has what as its degree? Kira? 3. Good. It's of degree 3. What are we going to name a function based on its degree if it's of degree 3? Sarah? Good. A cubic function. Okay? So this is going to be cubic. Okay? Now there's another way we could name the function. Okay? We could name the function instead of by its degree by the number of terms that are in our polynomial. Does anybody know what we would call this based on the number of terms that it has? Ian? No. Good guess. Good guess. It's kind of a trick question. I mean, I'm not trying to trick you. I'm just trying to make a point. Carson? No. All right, so if it has 1 term, we called it a monomial. If it has 2 terms, we call it a binomial. If it has 3 terms, we call it a trinomial. And all of them after that, we just call polynomials. Yeah, so that's as good as I can get right now, okay? I wasn't really trying to trick you, okay? I'm trying to just make it stick in your head a little bit, all right? Yes, Foster.
3 would still be considered polynomial
2 and 3.
Like
The
two
numbers.
terms and two.
Yeah, they're still polynomials, but they have a more specific name they can be named by. It's kind of like numbers that are real numbers, but then they might fall into the category of rational or something that's nested within that. All right. So we're going to look at each of these pictures. We are going to determine not if the function is even or odd. That's a whole different conversation you're going to have in pre-calculus. We are going to determine if the degree of the function must be even or must be odd based on what we know. And then we're going to say how many real zeros we think each polynomial has. Who can tell me about the graph that they see in part A? Hasn't talked to me yet. New person? Nobody new else talked to? Jonathan, you have. Go ahead. So tell us about if it's even or odd degree.
It's even degree because it has 3 turning points.
Good. So he said it's even degree. He talked about the turning points to justify that, which is good. But remember, the turning points could be deceiving because they don't have to turn around any certain number of times. What else in this picture should tell you that this is a function that has an even degree? Aoife? Good. The end behavior is the same. Okay? All right. How many real zeros would this function have? Hannah?
It has 3, but it could
Good.
have 4.
Okay. Good. This function has 3 real zeros because I see it hitting the x-axis at 3 different places. It could have more, but we're just identifying the real zeros that we see. Okay, part B. Somebody tell me, even or odd degree? Daniel. Good. What's of even degree? Okay, somebody else. How many real zeros do you see this function having? Joseph. Good. Okay. I don't see any real zeros because it's not hitting the x-axis. Is it possible for a function that is of odd degree to have no real zeros? No, because what happens with an odd function's end behaviors? They go different directions, so no matter how high you move it or flip it over or move it down, one of those ends is going to eventually reach that x-axis, right? So with odd ones, we would have to have at least one. All right, part C, who can tell me degree? Sarah? No? Okay, sorry. Ellie? Good. So this would have an odd degree. This is not an odd function, but it is a function that must have a degree that is odd because of the way I see the end behaviors. How many real zeros would we see for this function? Kira? Good. Okay, so we see 2 real zeros. Oops. All right, so we're okay with this idea. Okay? Kind of generally looking at functions, not very specific. All right, it doesn't look like I changed the screen, but it did. Okay, so same graphs, but this time we want to estimate the turning points for each graph. Okay, let's just do this for one of these so we can make sure we can have some other conversations about end behavior. Kira? What's that? Okay, so the number of turning points that this graph has is 3, and we want to estimate the turning points. So we're going to say here's 1, and here's 1. And then I need to list those turning points. So if we're estimating, I'm going to call this first turning point negative 2.5, negative 4.5. Again, I'm estimating from visually how it looks on the graph. Okay. This second turning point is maybe at 0.5, 2.5. And then this third point looks like it's at 3, 0. So is this okay if anybody asks you to estimate the turning points? Yes, we're just literally finding the points where the graph turns around and writing what we believe their coordinates to be. Okay? Are we good? All right. Intervals where the graph is increasing or decreasing. Okay? So here's what we're going to look at. We read a graph from left to right. Let's look at graph C for this. Okay? If we're reading a graph from left to right, and you think about traveling on this graph, so the graph goes down here somewhere, here I come, I'm traveling on this graph. Currently, is the graph increasing or decreasing? And now? Okay. And then it hits that turning point again, and then? Okay. So, I have to be able to tell somebody, oh, from here to here and here to here is where it's increasing. So a way that we do that is using interval notation, okay? So an interval is basically a set of parentheses. Sometimes it looks like an ordered pair, but don't confuse it, okay? That says basically from here to here. Instead of saying, like, x is sandwiched between 5 and 2, I would say x is sandwiched between 5 and 2. It can't be equal to 2, but it can be equal to 5. Okay? So it's just like some brackets surrounding two numbers, and it means that what you're talking about is between these two numbers. Open, like a parentheses means like an open or not equal to. A bracket means that it's equal to. Okay? Now, given that this graph goes off, I'm going to kind of assume here that this graph goes forever, and we'll assume a stopping point here just to make a point. So this means from the left forever, it's increasing, 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 and I'm just going to look at the x-axis. For this x, still increasing. For this x, still increasing. For this x, still increasing, until I get, say, to here. What do you guys want to call it, like 1.2 or something? Sure. Okay. So until I get to 1.2, my graph is increasing. So I would say this graph is increasing from negative infinity until 1.2. Okay? Now, infinity is an idea. Okay? It's not a technical number. So we always use an open parentheses with infinity because you can't ever technically reach it. Okay? And we'll talk more about increasing and decreasing and whether you actually consider 1.2 part of it or not. For now, we'll just go ahead and use a closed bracket there, meaning we'll include it. Okay? Notice the numbers that I put in here were related to what on my graph? The x's. I was saying for all of these x's until you get here, the graph will be climbing up, right? But then you get to this x, and all of a sudden the graph isn't climbing up anymore, right? Then it's going down. But does the graph climb up again? Ooh, then I got to list another set of numbers in my increasing list, right? So let's say it increases from here to here, okay? Again, I'm listing x values. Those points correspond to what x values on the axis? From 3.5 to 5.5. For those x values, again, the graph is increasing. Is that okay with everybody? So again, I say, okay, from 3.5 to 5.5. And since we're not using infinity this time, we'll use both brackets. Now, to tell somebody that during this time and during this time, it's all increasing, you will oftentimes see people put a little u in between there. The u stands for like the union of the two sets, like this plus this other area. Okay? Is this all right with everybody? So instead of inequalities, all we're doing is listing the beginning and end, and instead of less thans and greater thans, we're just closing it in with a bracket. We know it's in between these two things. Okay? A bracket means it can be equal to a parenthesis not.
You already have, say you were asked to show where it's increasing and decreasing.
Yeah, that's what we're doing next.
If you use brackets on like 3.5 and 5.5, would you not be able to use
Yeah, we're going to let you guys just do that right now. We're not going to be picky about that, and then we'll delve more into why you can and why you can't do that a little bit later, like what more proper notation is, like editing it. So for right now, if it's a number, we're going to let you guys use the bracket, okay, for increasing and decreasing. So for decreasing, it was decreasing from here to here. On the x-axis, that was from our 1.2 until our 3.5. So our decreasing is going to be from 1.2, oops, wrong. Sorry, I need to erase. Until 3.5. So two ideas are happening here. So try to check yourself for a minute and see, do I understand both ideas she's talking about? And if not, which one is it that I don't understand? First, do you understand how to identify where a graph is increasing or decreasing? So can you tell where a graph is increasing or decreasing? Okay. The second thing is, do you understand that to tell somebody where this is happening, we just tell them places on the x, and then we're trying to use a new notation here called interval notation. We can also use this notation for domain and range, and we'll do that later also. Okay? So is everybody all right with increasing and decreasing? Foster?
Why is it that we used it goes to negative infinity when the graph is going down, but we didn't say it goes up to positive?
Because this one had a clear endpoint and stopped, and I said because this one went off the paper, we're going to assume that it keeps on going forever. Okay? All right. The other thing I want to talk about is end. Yeah, sorry, Kira.
You mentioned like using the X values.
Uh-huh.
Why do you like it?
Uh-huh. That these numbers are only based on the x-axis. So if the graph is increasing from here to here, I'm looking at this x till this x or whatever and saying that's the area where it's increasing. Is that okay? Okay, now your book is going to ask about end behavior, and here's what your book is going to say. If you had a problem like A and it asked about end behavior, here would be your book's answer. Up, up. All right. Okay. Now, they're assuming you're looking from left to right. This is totally not mathematically correct. Okay? And so, depending on the level of course you're in, maybe I care, maybe I don't care. I care in here because your pre-calc honors teacher or your pre-calc teacher, if you write up, up, they're going to laugh and they're going to mark it wrong, and that's going to be the end of it. Okay? So, we're going to learn a little bit of notation. Okay? And so, what we're going to say is this. Basically, you need to tell someone, here's where my graph goes, and it goes this way on the left side. Here's where my graph goes. It's going that way when you're on the right side. Okay? So first of all, f of x is the function that I'm graphing, right? And I want to tell them, what is it going to? Well, if I'm looking on the left side and the function just keeps going up, what's it going towards? Infinity. So I'm going to say my function goes towards infinity. Sorry, that's a really ugly infinity symbol, but you get the picture, okay? But I need to tell them that that's on the left side because it could be the same or it could be different on the right side, okay? So there's something that we put in front of this to note to people that I'm talking about from the left side, and this is what we do. We say the limit, because this is saying what is the limit of your graph. I'm basically saying it has no limit, right? Because I'm not saying it goes to 5 or it goes to 8. I'm saying it goes to infinity, okay? But I say the limit of my function goes to infinity. And underneath the limit, I write which x's I'm coming from. Okay? And this is as x goes to negative infinity. In other words, as you go as far left as you can on the x-axis, the limit of my function goes up towards infinity. So this is telling me about where to look on the x-axis. Look all the way to the left. And then this is telling me where does the graph go? It goes up, 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 because it's going to infinity. Does that make sense? Okay. So how do we think I would write it for the other side over here? If I want to tell somebody the end behavior on this side. Okay? Carson? No, we're not going to put the word max in there. Sandy? Good. This time the limit's going to be as x goes to positive infinity, because where do I want them to look for the x-axis? Way to the right where the numbers would just keep getting infinitely bigger on the x-axis, right? So this part is saying, look all the way to the right of the graph as x goes to infinity, as the x-axis just keeps on going out there forever, okay? Look at your function. Remember, f of x is like y. What happens to the y value of the points as the x just goes way out here? If you keep going way out here, where are you going to find your y values for your points? Yeah, way up high, right? And they're going to keep growing forever. So we say those y values are going to end up going towards infinity. Okay? So always the left side is going to have this part of it right here. And always the right side is going to have this part of it right here. The part that's going to change is what you write right here. All of these graphs, their end behavior either goes towards infinity, or what would be the other option? Negative infinity if the graph went downward forever instead of upward forever, okay? So like this graph over here, the limit as x goes to negative infinity, in other words, way on the left side of the graph, this graph ends up going towards negative infinity, okay? But if you take the limit as x goes to positive infinity, in other words, when the x-axis goes way out here on the right, this function goes towards positive infinity because it grows. Okay? Yeah. The ones that we're going to be working with, yes. So I understand some of the ones here had endpoints, so like this would be hard to say for this one unless we had like an arrow going on there. But the functions that we're going to graph are going to be like what you plugged into your calculator. They are going to have turning points, but they are going to keep going on forever because they are polynomial functions. Okay? All right, so homework.